All right, so second part of 11.7, our last set of notes, our last lecture for the semester.
Then video lectures next semester.
Yeah, I could just replay all the videos from last year, right?
You're pretty much done being a teacher.
Spherical.
Spherical.
All you have to do is pause the video and answer a question.
The other day in my geometry class, I misspelled isosceles multiple times. All right, so spherical coordinates is just another coordinate system that is useful when we're talking about 3D coordinates. So we represent our point. Our point is represented by three numbers: rho, theta, and phi. And we'll define what all of our coordinates are. Rho is the distance between P and the origin. So this is kind of like our radius. Rho is the distance between P and origin, and rho is always greater than 0.
Wait, how do you spell rho on here?
What's that?
Rho is the... Which one's P? Yeah,
up
there. Put a little stone on top of it.
Mr. Lopez is tail.
Yeah, that.
Yeah, I do P with this little top piece usually, and rho is more curvy.
So the first one should make it.
There's no double trace on that.
Right, there's no double
There's no second trace.
You put a tail on a row?
tail
You just
Let's
bottom
go
on the
Let's
like-
go E.
like foot, yeah.
this way?
The other way.
The other way?
Could you just write row phonetically?
That looks like a Q to me.
Yeah, that's definitely not rho.
Yeah, that's not a row. Row is, alright, I will try to make row,
I just
Why don't we just
italicized.
pinpoint you?
row is I make row more curvy. Row is more curvy than P. P is straight, row is curvy. Right. Alright,
Figure it out.
so row is greater than 0. So unlike polar coordinates where we can have a negative radius, rho is always greater than 0. Our second angle, theta is the same angle that we used in polar coordinates and cylindrical coordinates. So this is our same angle that we used in polar and and cylindrical coordinates. And in spherical coordinates, we're going to say that our r that we used in polar and in cylindrical, we're going to say r is greater than or equal to 0. And we'll draw a picture here so that we'll put get a visual for all of these. And 3, phi is the angle between the positive z-axis and the segment joining the origin and P. See how P is like straight and it has this little thing on the top? Rho is curvy. And phi is between 0 and pi. So phi is going to go from the positive z-axis, vary from the positive z-axis to the negative z-axis. So let's just draw a picture of these coordinates so we can get an idea of what we're talking about here. Here are my rectangular axes, the ones that we're familiar with. Oops, I don't want an arrow on the end there. So I'll do that, this. And then we'll draw in some dotted lines. And then label everything. All right, here we go. And this angle is phi. This length is rho. This angle is theta. This is our r in polar or spherical coordinates, so this would be r up here as well. This would be y, and this would be x. So there's what we're talking about, and this is our point up here. Rho theta phi. So questions on this. So our conversions from spherical, back and forth from spherical to rectangular, or spherical to cylindrical, all come from working with these right triangles here and here. So we're going to write our conversions, but they all come from working with this triangle here and the triangles that we have here in the XY plane. All right, so our conversions. Spherical to rectangular. Why do I don't like H's here? So x is going to be rho sine phi cosine theta. Y equals rho sine phi sine theta. And z is rho cosine phi. And that all comes from looking at this triangle and these triangles down here, like I said. And to go the other way, rectangular to spherical. See if I can get it right this time. Rho squared equals x squared plus y squared plus z squared. Tangent theta is y over x. And phi is the inverse cosine of z over the square root of x squared plus y squared plus z squared. And for most stuff we would be going from spherical to rectangular. We'll have an equation in spherical coordinates. We want to figure out what it is we're talking about, what our graph looks like, that kind of thing. But occasionally we'll go from rectangular to spherical. And then sometimes you'll want to go from spherical to cylindrical and back and forth that way. So we'll write out those conversions also. And remember, we're saying that our r in cylindrical coordinates is greater than or equal to 0. So we're not allowing negative radii here. R squared is rho squared sine squared phi. Theta is theta. And z is just like our rectangular, rho cosine phi. And this we can also equivalently, we could write this as r equals rho sine phi. And to go the other way, cylindrical to spherical. And again, our radius r is greater than or equal to 0. We're just going the other way. Rho is the square root of z squared, r squared plus z squared. Theta equals theta. And phi is the inverse cosine of z over the square root of r squared plus z squared. And I did it again. All right. Maybe I need to make that my definition. This is spherical. So questions on our conversions. The way I usually think of the conversions, I'm like you probably know by now, I'm not a big on memorizing formulas. I tend to remember these and go the rectangular to spherical, spherical to rectangular, and then use what I know about those to go to cylindrical. That's just the way I go about it. If you ask me what these were other than these, I probably wouldn't be able to tell you, but I usually think of going back and forth from rectangular to spherical and then apply that to cylindrical. All right, any questions? Let's look at some examples. We're going to do some conversions. So our first one, we want to convert to spherical. X squared plus y squared equals z squared. So before we do our conversion, what is a graph of this? What is the surface? So Garrett thinks a hyperboloid of one sheet. Eric agrees. Anyone else? So if we look in the xz plane, if y equals 0, I get x squared equals z squared, or x equals plus or minus z. So what is that? 2 lines. So what is this going to be? Cone. This is our double mapped cone. So I end up with lines in the xy plane and the xz plane, and parallel to the parallel to the xy plane, if z is a constant, I end up with circles. So this is a cone. So we want to write the equation of a cone in spherical coordinates. So to do our conversion, what are we going to do? X squared equals rho squared, sine squared, phi, cosine squared theta. Y squared is rho squared, sine squared, phi, sine squared theta. And that equals rho squared, cosine squared, phi. Let me rewrite that. Yes. There we go. And then we want to simplify this. How are we going to simplify this? This is phi.
Divide by rho squared.
Okay, so we could divide by rho squared. Now, what are we assuming if we divide by rho squared? We're saying that rho does not equal 0, right? So we're saying rho is not equal to 0. So if we divide, so we're not dividing by 0. So we divide everything by rho squared. So I get sine squared, and let's factor out this sine squared here. Sine squared phi times cosine squared theta plus sine squared theta equals cosine squared phi. This is 1, so I get sine squared phi equals cosine squared phi. And how can I simplify this?
Tangent squared phi equals 0.
Tangent squared phi equals 1. Or tangent phi equals plus or minus 1. So where on my unit circle, where is tangent equal to plus or minus 1, tangent of my angle? Phi equals pi over 4, and for the negative? 7 pi over 4, or if we want to stay, we could say 7 pi over 4. That'll work. I can do that. So this is the equation of a cone in spherical coordinates. Phi equals pi over 4, or phi equals 7 pi over 4. So that phi equals some constant angle. That tells us we have our angle from the z-axis is constant. Questions on that conversion?
Mr. Beaver, can you go back to your notes really quick?
Yes.
Before? Did you, should the top one be rectangular or spherical and the second one be spherical or rectangular?
Use the top one when we were going to spherical.
Did I label them wrong? Spherical to rectangular? So this one, I guess, so if I were looking for x, y, and z, you could use these relationships. And if you were given phi and theta and rho, you could get x, y, and z from these. So I guess that's why I called them spherical to rectangular. And if you were given, if you're trying to find rho, theta, and phi, given x, y, and z, you could use these. But you can use either. If we're converting equations, we can use any of these relationships. All right. Let's look at another example. We want to convert to spherical.
So in this last example, what is
But so we're not looking for a point. We wanted to convert this. We wanted to convert this equation. We wanted the equation of this surface in spherical coordinates. Rho can be anything. Right, because the sides of our cone extend from 0 to infinity. And theta can be anything between 0 and 2 pi because we're going all the way around in a circle. That make sense? So part of what we're doing now is kind of getting our feet wet in thinking about how the different coordinate systems work, because in the second part of the second semester we'll be using the coordinate systems quite a bit, and we will want to be able to recognize, oh, pi equals pi over 4, we're talking about a cone. And if we're talking about a cone, then theta can vary between 0 and 2 pi, and rho can be anything. All right, let's look at another one. To spherical. We're going to go to spherical again. We have x squared plus y squared plus z minus 1 squared equals 1. So before we convert, what is our surface here? Sphere. I did it again. This is a sphere. Radius 1, center 0, 0, 1. So we want to write the equation of this sphere in spherical coordinates. So let's plug in our equivalents for x squared, y squared, and this quantity in spherical coordinates. So x squared is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. That's my x squared plus y squared plus rho cosine phi minus 1 squared, and that equals 1. Now we're going to simplify. So what do we want to do to simplify here? Factor. So let's expand, and we could factor. Now we could factor our rho squared sine squared phi here, and we have a cosine squared theta sine squared theta. So we just end up with a rho squared from these two terms. We just end up with a rho squared sine squared phi. If I factor that out, I just end up the cosine squared theta plus sine squared theta is 1. Plus, and we're going to expand this out, rho squared cosine squared phi minus 2 rho cosine phi plus 1. And that equals 1. And now what can we do? We can factor out a rho squared from these two terms, and then we have a sine squared phi plus cosine squared phi left over. So I end up with rho squared minus 2 rho cosine phi equals, and I'm going to subtract 1 from both sides, equals 0. And from here I'm going to say that rho squared equals 2 rho cosine phi And we're going to do what we did before and say we're going to divide by row, saying that row is not equal 0. So row, and assume the row is not equal 0, so row equals 2 cosine phi. And that would be our equation of this sphere in spherical coordinates. Rho equals 2 cosine phi. So in this is very similar to what we did in polar coordinates, where r equals 2 cosine theta. We knew that was a circle. So rho equals 2 cosine phi. That gives us a sphere in 3 dimensions. Questions on that one? All right, that's all I wanted to do today. So, homework. All right, there you go.